Hello, this video is going to walk us through one of the most complicated, difficult aspects of the course and absolutely the most useful, versatile procedure that there is, which is testing a difference between two populations. This is from 2010 question 5 concerning tropical fish. I'll give you a minute to read it. However, I'm just going to look for a difference in mean length rather than whether they're greater. Okay, well, before we proceed, the first thing we have to establish, above all else, is are they independent random samples? Are they independent random samples? And we can see from the question that random samples were selected, so we just say, as stated in the question, they are independent. The next big question is it reasonable to assume that these populations are normal? And this is not quite so obvious. The sample sizes are not sufficiently large for the central limit theorem to guarantee that they overcome any problems with the original population. So we need to do a bit more work before we can get to that point. Entering the data into the TI and using the stat plot functions allows us to see the box plot and the normal probability plot for both samples. We can see certainly from the box plot of the first data set that it's symmetric without any outliers, without any significant skewness. In fact, it looks totally symmetric. So that's good. And again, the normal probability plot is definitely linearish. So that leads us to conclude that the first data set does conform to a normal distribution. The second data set is a little bit weirder. There is some evidence of skewness in the box plot, and it's a little bit raggedy over here on the right hand side, but obviously you'd say that there's nothing overtly non-normal about them. There are no outliers. There is some skewness. There is some departure from normality, but nothing horrendous. So you would say that the data do appear to conform to normal distributions. So suppose xb represents the lengths of adult fish from Bayreuth, and we can see that we assume that they're norm distributed with a mean length of mu b and a population variation which is unknown. The population of adult fish lengths from Fish Friends again follows a normal distribution with a mean length of mu f and a population variance which is currently unknown. Our null hypothesis is that the mean length of adult fish from Bayreuth is equal to the mean length of adult fish from Fish Friends. Our alternate hypothesis is that these means are not equal. Therefore, this is a two-tailed test, and we'll have a standard alpha level of 5%. Given that the populations do appear to be normal, then according to theory, the sample standard deviation of 8 fish from Bayreuth should follow a normal distribution with a mean of mu b and a variance of sigma squared b over 8, and 10 fish from Fish Friends should follow a normal with a mean of mu f and a variance of sigma squared f over 10. So the difference in these means, which is what we're really testing, is, well, according to theory, combinations of normal random variables are themselves normal. So x bar 8b minus x bar 10f should follow a normal with a mean of mu b minus mu f and a variance equal to sigma squared b over 8 plus sigma squared f over 10. Assuming h0 is true, then mu b minus mu f should be 0 because we're assuming that they're equal. So this should follow a normal with a mean of 0 and a variance of sigma squared b over 8 plus sigma squared f over 10. However, the problem is that we don't know what the true population variances are. Therefore, we have to use the sample data as a best estimate of those. And we have from this that s squared b is 0.434 squared and s squared f is 0.550 squared. So because we're using the sample data rather than known population data, we need to use a t-test. Generally, that is with n-1 degrees of freedom. Obviously, the 8 Biorite sample means we have 7 degrees of freedom, and the 10 Fish Friends sample means we have 9 degrees of freedom. So altogether, we have 7 plus 9, which is 16 degrees of freedom. So now we can carry out the test. Technically, we could go straight to the test and work out what the t-statistic is. And the formula book and the course tells us that the t-statistic is observed difference minus the null hypothesis value divided by the standard error. Well, the standard error is the square root of the variance, and the variance, well, is the best estimate of population b over 8 plus the best estimate of population f over 10. So we end up with 3.40 minus 3.46 minus 0 divided by the square root of 0.434 squared over 8 plus 0.550 squared over 10, and this gives us an answer of minus 0.259. Looking at the t-distribution tables, 16 is listed, and for a 5% significance level that is 2.5% in either tail, and that gives us a critical value of 2.12. In other words, if the test statistic is further than 2.12 standard deviations away, then it will be significant. So 2.12 up at the right tail and minus 2.12 down at the left tail, and our test statistic is here, minus 0.259, clearly in the main body of the curve, clearly nowhere near the critical values, and therefore there is insufficient evidence to reject H0. If we actually did this on the calculator, it would tell us that the p-value is 0.3996. A p-value of 0.3996, basically 40%, says the probability of getting an observed difference further away from 0 than what we have as a natural consequence of the null hypothesis actually being true is 40%. 40% of the time we would have observed differences more extreme than what we have, when in fact there was no real difference. So, the sample data do not provide convincing evidence to conclude that the mean length of the adult fish of the species from Fish Friends is any different than the mean length of the adult fish of the same species from Biorite. So, there you go. The calculator will go straight to the test and you can get this information straight away, but the purpose of this video tutorial was to really walk you through and help you understand how this is actually built and constructed.